Good afternoon and welcome to the first webinar that we hope will be a regular series. My name is Kamran Khajapour. I work for AXT as a microscopy product manager. For those who are not familiar with AXT, we are an Australian-based company representing over 30 manufacturers. And in fact, we are the largest independent company distributing scientific instruments in Australia and New Zealand. We operate in many different markets, including material science, life sciences, non-destructive testing and mining. It's been always our mission to bring you the cutting-edge scientific and analytical tools to facilitate your research. So please feel free to visit our website to make yourself more familiar with what we do and what is our broad product range. One such example is Delmic, that we've been working with for more than 2 years now. And Delmic are based in Netherlands. They are developer of truly innovative and cutting-edge technology combining light and electron microscopy. And their products are completely unique in the marketplace. Today we look forward to introducing you to the SPARC, which is their Cathodoluminescence detection system. If you don't know what it is or how it will benefit your research, just stay tuned, as we are going to tell you all about it in the next half hour or so. Now, just before starting the main presentation, I'd like to mention that you can raise your questions at any time during the presentation with using the chat box or the Q&A part in the bottom of the screens. Now that probably you are sick of listening to me, I'd like to introduce today's presenter, who is Dr. Ton Cohen, whom some of you might know from his previous talks in Australia. Ton is Delmic's in-house SPARC application specialist. He studied at University College of Utrecht, did his BSc and master's degree there before joined Albert Pullman's group in Amsterdam at FOM Institute Amolf, where he co-developed the SPARC system for the first time, and then joined Delmic to commercialize the product, and it's been a very successful product since. So I leave it to him with his presentation that I'm 100% sure you're going to enjoy and learn a lot from. Over to you, Tom.
My name is Ton Koenen, and in this webinar I will talk about angle-resolved cathodoluminescence and how it can be applied to different application areas such as material science, geology and nanophotonics. Here's an outline of what I'm going to discuss in this webinar. First I'll briefly introduce our company. Then I will talk about the physical background of the cathodoluminescence processes and how it comes about. Then I will discuss how you can actually detect cathodoluminescence. I will show some examples of different applications, and then I will end with an outlook. Delmic is a spin-off company from the Technical University in Delft and the FOM Institute Amolf in Amsterdam. And in particular, it is a spin-off from the academic groups from Professor Pieter Kruijt and Professor Albert Pullman. And in both these groups, they have in common that they combine optical nanoscience or optical microscopy with electron microscopy. And this forms the basis of our company, Delmic. And so cathodoluminescence is an example of such a technique in which you combine optical information and electron microscopy. And cathodoluminescence starts with an energetic electron beam which interacts with a material, and because this interaction is so energetic, there are a lot of processes that occur simultaneously. There are secondary electrons that are emitted and backscattered electrons. If your material is thin enough, you can also perform transmission electron microscopy, but there's also emission of electromagnetic radiation. And because of the high energy of the incoming electrons, this ranges all the way from the X-ray regime into the visible. And so this is the part that we focus on in cathodoluminescence. And in fact, the definition of cathodoluminescence is the light ranging more or less from the ultraviolet, visible infrared, by a free electron and so that's generated by a free electron. And the name really comes from the fact that free electrons also were used to be called cathode rays historically, and this is because, and this stems, say, from the fact that during experiments in cathode ray tubes, they would see light emission when they would apply a potential between two capacitors, and this led to the emission of electrons that were accelerated towards the tube walls of this vacuum tube, and that would give light, and this was called cathodoluminescence at the time, because electrons were not discovered yet. Now, the motivation of why cathodoluminescence is an interesting technique is shown in this slide, and so in here you see a gold nanorod. It's about 150 nanometers in length, and this structure has a strong interaction with light, and in particular with light of a 750 nanometer wavelength, which is infrared light. And in fact, the size of such a wave, or the wavelength, is shown here to scale, and as you can see, it's much bigger than this structure. But this also presents a problem, because this structure has the ability to confine this light wave very close to the particle. But if you want to study that phenomenon, you are limited by the diffraction limit in an optical microscope. And so the diffraction limit is shown here, also to scale in this red circle, and this represents the limit to which you can resolve details with an optical microscope. And so on the other hand, you have electron microscopy, in which you can readily focus highly energetic electrons to very small spots, as indicated on the right. And but normally in electron microscopy you focus on the topography of your material, or the geometry. And so cathodoluminescence really combines the best of both. On the one hand, it combines on the one hand you have the high resolution of the electron microscope, and on the other hand you have the functional optical information that you get from optical microscopy. And by combining these, you have a very powerful technique that can be used for a large variety of things. Now, although the definition of cathodoluminescence is rather simple, it is in fact an umbrella term, meaning that there are various physical processes that lead to light emission in materials, and there's not a single process that does that. And so these processes are divided into two subcategories, say. And the first one is referred to as incoherent cathodoluminescence. And in that case, the electron beam hits your material and interacts with your material inside. And so the electrons are decelerated in a volume inside of your material. And while it decelerates, it transfers energy to the material, and this energy is used to promote valence electrons in the material to an excited state. After a certain time, this can decay with the emission of a characteristic photon. This photon is then called cathodoluminescence. And this process is very similar to photoluminescence or fluorescence, except that the electron is used to do the excitation, the electron beam, rather than a laser beam or an LED light source. And so this is a difference. And another difference is that a laser is normally monochromatic, meaning that you excite it with a particular energy, but the electrons can be considered white, and so that they can excite all the transitions that are available. And then, so the size of this volume that can be tuned with the acceleration voltage in your microscope, and this can be used. And so this form of radiation is well known from also the cathode ray tube televisions, where electron beam was also used to create color television by irradiating different materials with a specific quantum mechanical energy structure that gives rise to the emission of particular CL colors. And so This process can also be quite efficient because the primary electron has a lot of energy, and so it can generate multiple photons per incoming electron. So that is the first category of cathodoluminescence. Then there's a second category, which is referred to as coherent cathodoluminescence. And that is more easily understood from an electrodynamic perspective, where you consider the electron to be a moving charge. And while this charge is moving, it has electromagnetic fields that move along with the electron. But while it's moving through free space at a constant velocity, these fields, they remain stuck to the electron. They're what is called evanescent in electrodynamics. And but when this electron is perturbed, for example, by a change in the dielectric environment, and this can, for example, be an interface with a vacuum and a material, as indicated here, then these fields can decouple from the electron, and with that they can radiate directly, and this is called the transition radiation. And then this charge can also couple to other electromagnetic modes that are available, such as surface plasmon polaritons, which is a hybrid between light and movement of the conduction electrons in a metal. And so, there are various ways in which this excitation can be used, and in particular, it's also sensitive to the local density of optical states, which is a key quantity in optics. And so the electron senses the number of states that are available, and the amount of energy that is transferred, or the probability that energy is transferred, depends on that. And so it can be used to map this quantity, the local density of optical states. Now, why is it called coherent? And so that is because the light that is emitted has a phase relation to the electric fields of the incoming electron, whereas in the incoherent case, this phase relation is lost, and that's why that is called incoherent. And note that the coherent cathodoluminescence process is much less efficient than incoherent cathodoluminescence in most cases, and so it's always there, but it depends on the material that you're looking at, whether you can actually see it. And so in metals, the coherent form of cathodoluminescence is dominant, because the incoherent form is completely damped, because metals, they don't exhibit fluorescence normally, because because of the closed band structure, everything is dissipated as heat. But in a direct bandgap semiconductor, or in a phosphor material, or in a geological mineral, the incoherent cathodoluminescence dominates the response. So how does CL compare to other techniques? And so I would say that it is complementary. And so there's you have in SEM, you have SE detection, which you can use to study surface topography or the geometry of your sample, and maybe you have a little bit of material contrast. But this material contrast is more pronounced in backscattering imaging, where you have or you can see changes in density or atomic number. And in EBSD, you can even look at the crystal structure and the crystal orientation of your surface, but it is a little bit more complex as a technique. And then you have X-ray detection, WDS and EDS, where you look at a large energy or high energy regime, so in the order of hundreds of electron volts to kilovolts. And in that energy range, you are sensitive to core transitions. And that can directly be linked to the composition of your material. In cathodoluminescence, you're looking at the energy range from, say, 0.5 to 6 electron volts. And in that energy range, you are sensitive and also to composition, but also to a lot of secondary effects, such as crystal structure and bonding. There are band gaps in the visible part of the spectrum. You are sensitive to trace elements, dopants, defects, optical resonances, refractive index. And so there are a lot of things that you can study in cathodoluminescence. And so if you know how to apply the technique and know how to disentangle these different effects, it can be a very powerful technique, complementary to what is already done in SEMs. So this gives me an opportunity to check if there are any questions. And there's one question, which is, so somebody is asking whether it's necessary to have a field emission gun for coherent cathodoluminescence. And this is not the case. And so the coherent cathodoluminescence can be observed for any type of electron gun. And so the coherence really comes from the fact that the single electron is coherent with the electric fields of a single electron are coherent with the light that is emitted. And the coherence of the electron beam itself is not so relevant in this case. And so you can also see it for tungsten tips or for lab 6 tips. There is still a benefit for using a field emission gun in some cases, because this interaction is really localized, and that means that if you want to profit ultimately from the high spatial resolution, the field emission system will give a better result, because it can focus. It usually has a better focus than a tungsten or lab 6 system. So yeah, now we'll move on to the explanation of how you actually do a cathodoluminescence detection and what the system of Delmic actually does, the SPARC CL system. And this you see here. You see a picture of the system. And so here you see a scanning electron microscope. And so the RCL system, the SPARC, is an add-on to SEM. And this SEM can be from different vendors. It doesn't really matter. It can be different models also. And our system is mounted on that. And it consists of two parts. One part here is the part that collects the cathodoluminescence inside of the vacuum chamber. And this part directs the light towards the detector, which you see here. And this is the part where you do the light detection, and this is then connected to a computer where you can do where you can control everything. So first about the light collection, and so we use a high numerical aperture paraboloid mirror, and as you see here. And this is the pole piece where the electron microscope, where the electrons come out, and here's your sample. And there's a small hole in the paraboloid through which the electrons can actually access the sample. And then, this collects the light and sends it towards the detector. And there are a couple of things that are important. And so our system is aimed to be very efficient at light collection. And so we achieve that by having a high numerical aperture. But even more importantly, we have a means to position the mirror very accurately. And so this high numerical aperture optic is very sensitive to misalignment, and it's a little bit like a microscope objective in that sense. And so it needs to be aligned with submicron positioning with respect to the electron beam impact position. And this requires micro actuators, and this is what our system can do. And so if you properly align your paraboloid, the light that is emitted will be perfectly collimated by the paraboloid, and this makes the collection and the detection later on much more efficient. So by doing this, you have an additional advantage. And so when it is perfectly aligned, the beam is perfectly collimated. And if you use a two-dimensional CCD array, you can actually image the full beam that comes from the paraboloid, and you can correlate different positions in the CCD image to different positions on the paraboloid, and those correspond to different emission angles. And this means that you can do a Fourier imaging or angle-resolved cathodoluminescence imaging, so you can measure the angular profile, and this can be highly useful also in several applications. Now the mirror, the mirror that you used, it covers quite a large solid angle, so this is nice for detecting a lot of light and being efficient at light detection. But it can also be nice to use your other detectors in the SEM. Sometimes those can be shielded by the paraboloid, and that's why the system is retractable. And this is and so the nice thing about the collection optics is that it can both do the micro positioning, but it is still retractable. And I can show a movie here of what it looks like. And so here you can see it move, and now it's like at the sample position. And so this is how it would be when you do cathodoluminescence. But then you can always move it out if you want in situ and do other things that you would normally do in the SEM. So then on the other side, you have the detector, and the detector does the CL detection. And so this is aimed to be very modular. And so there's, in the front here, there's optics. And in particular, this optics can be optimized for specific wavelength regimes. And this comes in the form of these modules. And inside these modules, you have the optics, but you also have a calibration light source, which can be used to calibrate your system in terms of wavelength. And these modules, they can be interchanged easily, and they're automatically recognized by the system. And this means that you can, the system becomes very modular, and you can just switch from doing ultraviolet measurements to infrared measurements by switching these boxes, and still have an optimum performance. And then, furthermore, there in this optics compartment, there's also a possibility to perform fiber coupling, and so then the CL light will be coupled into a fiber, and then you can do other, guide it to another detector or whatever you would like to do with it. And then there's also a possibility to have a photomultiplier tube present there for a direct intensity mapping. And I will come back to that later and explain what that is. And then in the back, you see the spectrograph, and the spectrograph can be used to perform a spectroscopy. For spectroscopy, you can choose different detectors optimized for specific wavelength regimes, with specific sensitivities. But there's also, you can also choose the gratings, and those can also be swapped easily. And so the diffraction grating in spectroscopy determines for which wavelength regime you are optimized, and it also determines the spectral resolution that you can reach. And depending on the application, you may want to play with that. Now, this is the big SPARC system, but there's also a more compact system, and that it does not have the spectroscopy part, so it's smaller, and so it's a more compact version than the one that does the spectroscopy, the SPARC spectroscopy. Now, everything is controlled by software, and so the software includes hardware control, data acquisition, data correction, analysis, export, and so all the things you want from the software are present. But this software is also open, and so you can also do scripting or write plugins, and this allows you to do non-trivial things or things that are not so common for CL imaging. And so, as I mentioned, you can do intensity mapping with this photomultiplier tube module. And if you do intensity mapping, you put the beam in a position, then light is guided towards the detector, and then there's also a filter wheel in front, so you can either choose to let all the light go onto the detector, or you can choose a specific band. And then you will get one data point, and this is what is called the cathodoluminescence data cube, where in the vertical direction here you have wavelength or color, and in the two other directions you have X and Y, and this data cube represents sort of the CL data. And when you do intensity mapping, you can collect for one specific position at a time, and one specific wavelength at a time, you can collect the data. And when you scan the beam, then you will collect another point, and that way you can make a two-dimensional image for a specific wavelength. And this can be rather fast because these photomultiplier tube detectors, they can be read out quickly. And so you can make a large image with a large number of pixels quickly. And then if you change the filter then you can also do that for a different wavelength and yeah, try to construct a more complete data cube. So this is intensity mapping. Then you can also do hyperspectral imaging. And in that case, the light is directed towards the spectrograph, and there's a pixelated camera in there with a CCD or a CMOS camera. And like there you have a grating which decomposes the cathodoluminescence into different colors and directly projects that onto this camera. And that allows you, for every position, to directly collect full spectrum. And so you collect an entire column of data here in which the spectral resolution can be high. So it can easily be sub-nanometer in terms of spectral resolution. And then by scanning the beam, you can collect multiple points. And then, here you see an example of such a hyperspectral image where you can plot the spatial distribution for a particular wavelength. And this is all derived from the same data set. And so you can do that for different wavelengths and see how the spatial distribution changes. And so what is also interesting to note is that you can, while you are acquiring cathodoluminescence, you can always acquire also the secondary electron signal. And this allows you to directly correlate the CL signal to the SE signal, or the and maybe say something about the geometry of the structure as well. Then in angle resolve detection, you have, as I mentioned, you collect an image from the full a beam that comes from the paraboloid, and that you see here. And so this is the paraboloid mirror that you're looking at directly with the CCD. And each point in this image corresponds to a unique emission angle, but there's still a mathematical conversion that needs to be done in order to get an angular profile. And this can be done. And this is what such an angular profile typically looks like. And so in this profile, you have in the center here, you have the direction which corresponds to normal emission, so normal to the substrate. And then the subsequent rings correspond to different zenithal angles. And then in this direction, you have different azimuthal angles. And so this is, and so there's also a part which is missing here. And that's the part where the paraboloid is open. So this part you don't collect. But in the rest, you see the angular profile. And in this case, this is a gold substrate. And for gold, you see this donut type pattern, or toroidal emission pattern. And this is characteristic for gold. In fact, it's this transition radiation that I talked about, this coherent form of radiation. And you can make a crosscut through such a pattern, or through this pattern, and then you can see that nicely matches the predictions, because there are small changes as a function of wavelength. And you can see those with the technique. And the wavelength specificity it also comes from using a bandpass filter. Okay, so next are the applications. I will take the time again to briefly look at some questions. And so there are two questions. One is the fiber coupling. And so the fiber is free to choose. And so we just have an FC coupler that can be used for where you can mount your fiber, and so this can be whatever you like. And so the core diameter that is supported is something like 100 microns and larger, say, you can even use a multi-mode or multi-core fiber with multiple fibers to increase the incoupling aperture, and so that can be useful in some cases. And the sensors that we use, the CCD arrays and the CMOS arrays, those are cooled because the performance is much better if they are cooled, but they are Peltier cooled, not with nitrogen. and so they just need to be plugged into the socket, and we supply actually liquid cooling, because Peltier cooling can be done with either with a fan or with liquid. And if you use a fan, you induce all the vibrations in the SEM, because a fan is a moving object. And if you use liquid, then it is better. And then there's another question whether the sample can be rotated during measurement. And the answer is yes. You can rotate your sample during measurement with the SEM stage, or you can also rotate the scan direction of the SEM. And so most SEMs, you can also rotate the scan direction. And so depending on what you're doing, that can be good enough. And so for hyperspectral imaging and for photomultiplier tube imaging, intensity mapping, you can rotate the scan direction. For angle resolved imaging, where the orientation of the sample with respect to the paraboloid is actually important, then you can physically rotate your sample. Yeah, so I hope that answers the questions. And so now we'll continue to the applications. And so cathodoluminescence is a very generic technique, a very generic microscopy technique, and as such it can be applied to a wide range of materials. And so historically has been applied a lot to geological materials, and in the material science for semiconductors, for ceramics, for example. But more recently, it has also been used a lot in nanophotonics and plasmonics, and so studying nano-sized objects that manipulate light on small length scales, where it is difficult to use optical microscopy because structures are so small. And then one thing that's not shown here, but there's also quite an interest in studying softer materials, biological tissue, and there it is. The challenge is to have a sample that is stable enough to do proper imaging. And so in these cases, in geology, material science, and photonics, the materials are inorganic and they're very stable. But in softer materials, the electron beam can be damaging, and so there you have to you have to work on the sample preparation. But even there's a lot of progress being made, and there are already examples of very nice examples, in fact, of cathodoluminescence being used for biology. Now, so to go a little bit to dig a little bit more into that. And so this is the wavelength range that's typically covered in cathodoluminescence, 200 nanometers to 1600 nanometers. And here are some particular application areas that are of interest. And so in the infrared, there's a lot of interest in photovoltaic materials, integrated photonics. And then in the ultraviolet, there are wide bandgap materials, UV sources. And then in the visible, phosphors and biolabels, for example. And there's some topics that span the entire detection range of the cathodoluminescence, such as minerals, ceramics, LEDs, plasmonics, metamaterials. And so here you see an example of some spectra of measured with cathodoluminescence on variety of these types of materials with technological relevance also. And so here's an example from geology measured with our system. And so on the left here you see an SEM image of a zircon crystal. And zircon is a mineral. It's known to be very resilient to weathering, and so it remains in the Earth's crust for a long time, often. And in these zircons, when they grow, they are subject to small changes in the growth conditions, and sometimes they remelt a little bit, and the composition of the magma from which they are formed changes slightly. And this leads to zonation in the growth, but this is not visible in SEM. And so the SEM is really uniform. If you use backscattering, you see a little bit more contrast, but in cathodoluminescence, you see a really rich contrast, and this is what you see here. This is a composition of 3 intensity maps measured with different color filters. And what you can see here these rings, and that really corresponds to the different growth rings in this zircon. It's a little bit like a tree in that sense. And this can be very efficiently visualized with cathodoluminescence. It's very quick. And why is that important? And so these zircons are very useful for dating rock, and in particular they can be rich in heavy metals such as uranium, and these can be used to date the rock, and this can be used to date back in a very long time, billions of years. And so the combination of having these heavy metals and also having the resilience to remain in the Earth's crust for so long makes them interesting for that. But with mass spectrometry is a rather slow technique, so that mass spectrometry is used to do this dating. And so you need to choose a specific spot. And cathodoluminescence can be used to identify which spots are useful or interesting. And so it is often used as a pre-screening technique, essentially. Then I have an example from material science, in fact, from the semiconductor world. And so in this case, we were looking at gallium nitride, and gallium nitride forms the basis for LEDs. And almost all the LEDs you find in cars or in ambient lighting, televisions, cell phones, it's made of this material. And if you have a bulk LED substrate with, normally there are quantum wells inside with a little bit of indium. And there you have very uniform blue peak, as you would expect. Now, there's a major problem in these types of LEDs, and that's that because it is a high index material, a lot of the light remains trapped inside of the LED, and this can only 20% or less comes out, and this can be improved by structuring the LED. And in fact, the same goes for solar cells, where you have the inverse problem, and so there it's difficult to get the light in. And so, and in both cases, nanostructuring can help. But if you do nanostructuring, there are quite a few other things that can happen. And so here's an example of a nanostructured LED device, or structured in this case. And if you do hyperspectral and look at and here this is false colored to indicate color differences in the cathodoluminescence, you can see that there are quite a few color variations inside of this structure. And this is because of growth defects and changes in the growth conditions that lead to an uniform emission. In fact, so here I put some numbers, and here you see that on these different positions, the emission spectrum can vary quite a bit. And this is not desirable for an LED. You want to have a single emission wavelength like the structure I showed. And so this indicates that there's still some imperfections. And so for improving these types of devices, it's very useful to probe them and to probe their properties on small length scales. And for that, cathodoluminescence is very valuable. Another thing that is particularly nice in these cases for gallium nitride is that gallium nitride is a wide bandgap material. And so it is quite easy to excite with electrons. But if you want to do it with laser, you need an ultraviolet laser, and this can be challenging, more challenging. And so with electrons, it's very easy to excite. Then I have an example from nanophotonics, and this is in particular from plasmonics. And plasmonics is the study of metallic nanostructures that interact with light, and in here, I show an example of a patch antenna, and this is borrowed from the radio frequency regime, but then shrunk to the nanoscale, and so it consists of a 20 nanometer thick gold disc with a small spacer layer, and then a gold ground plane, which yeah, it can be used to interact with the patch on top. And then, so within this gap, you have a very strong electric field, which can be used for sensing potentially. And then this antenna will direct the light in a particular direction. And so in this study, we studied the different diameters. And so one thing that is important in this case is that this disc, it acts as a resonator. It acts as a sort of organ pipe where waves rattle around these plasmons, which are bound to the metal. And as I mentioned, plasmons are a hybrid between a light and a conduction electrons in the metal. So light that just really sticks to the metal interface and then propagates along the surface. And you can image that this resonant behavior, and so you can see here these different rings for different wavelengths. This is derived from a hyperspectral map that we took, and yeah, this can be imaged with the electron beam, and so tells you something about the resonant characteristics of this structure. And then because it is an antenna, only the standard wave pattern inside of this resonator is important. Also the angular profile, and this is a mosaic of angular profiles measured for different diameters and also for different wavelengths. And you can see that the antennas become larger in size, and you move to wavelengths that are more in the infrared. The structure becomes more directional, and this is yeah, this is what you expect based on the size. And something that can be measured. And so you can characterize the performance of your antenna in terms of directivity by measuring the angular profile. And in fact, you can go one step further with this. And so you not only can you measure the angular profile at a specific position, and so all of these were measured when the electron beam was in the center of the structure, but you can also move the electron beam across the structure and then look at how the directivity changes. And so you can move from the center to the edge, for example, as is shown here, and you can see clearly that the directivity changes when you change the position. And this is very nice that you can do this, because these structures, they're intended to be used as antennas that interact with point sources, with dyes, quantum dots, and nanodiamonds, and the electron beam can be used to simulate sort of a point emitter and see what happens when you move such across the antenna, and so with a very fast and simple way, and furthermore, you can measure also over different wavelengths, and so you can very easily probe the performance in that sense. So maybe this is so this was sort of the overview of applications that I wanted to give. And so this is not a complete overview of what you can do with cathodoluminescence. And as Kamran already mentioned, there's probably also going to be a continuation of this webinar format, and so there will be other webinars as well. And these things here could be maybe topics of those webinars. And so there's interest in three-dimensional imaging, tomography, there's already a possibility to measure a polarization of emission, which is another degree of freedom in light that can be exploited to learn more about your structure. Cathodoluminescence is a nice technique, but it is sometimes it's very useful to correlate with other techniques, and so using CL and in combination with a range of other techniques gives a more complete overview of your sample, in some cases necessary to give the desired result. So extending the wavelength range of CL, measuring in the deep ultraviolet, and moving towards the infrared. Performing larger scale imaging and automated imaging to and tiling and those kind of things to have a more automated approach and to cover larger areas. And then last but not least, there's a lot of interest currently also in studying the dynamics of cathodoluminescence. and doing ultra-fast spectroscopy. And this requires a pulsed electron gun, which can either be done with lasers or with electrostatic blanker. And this also gives adds a whole new dimension to cathodoluminescence studies. And so with that, I'd like to end. And so if there are, I will get to the questions after this. But if you have any afterwards, you think that you have any other questions or require information, then please visit the website or contact us if you want. And so let's see if there are any further questions. And so there's a question on the speed of acquisition for hyperspectral mapping of zircons. And so I guess in hyperspectral imaging, you are mostly limited by the camera readout rate. Because in zircons you have a lot of signal at your disposal, and so typically I would say that the speed of a spectrum or the spectral acquisition for a zircon, you need about 1 to 10 milliseconds per pixel to get a decent spectrum. Because the field of view is a little bit more limited when you do spectroscopy, you also need to scan the stage at some point to tile the spectroscopy maps together. I think the video, so I hope this answers the question. And so then there's a second question that somebody missed the initial part of the presentation, and I think the full webinar will be available later on. Yes, so I think, I hand it back to you, Kamran. Do you have anything to add?
Thank you very much. It was a great presentation, and thanks everyone for listening. So is there any other question that you guys would like to ask now? If not, I have one simple question from Tom. So is there any restriction of installing this instrument on SEM? So what sort of SEM do we need to have this system on it?
Yeah, so there's not really in terms of brand, for example, there's no restriction.
Okay.
And also in terms of model, there's no restriction. Sometimes the space can be an issue, and so this is something that needs to be looked at. And so some SEMs have really small chamber, and that can be difficult. Although in some cases that can still be solved. But also the configuration can be important, and so SEMs are configured in a particular way, and there are also other components that are mounted, for example, EDS, EBSD, and so on. And it needs to be somehow it needs to this all needs to be merged together. But in most cases, this is easy to fix, and so so we look at the design and we make it fit. So so normally there are no restrictions. Perfect.
Okay. And another question that I had. So this instrument, as far as we know, is available in 3 different levels. Am I right? So the base, can you explain that as well a bit?
Yeah, so it is quite open to configure, but say roughly speaking, we have so the most simple version is the SPARC Compact, which you can only do the intensity mapping, and then for the spectroscopy, there are a couple of types, and so there's the simplest version does spectroscopy and maybe also intensity mapping, and then then there's an intermediate case where you can also do angle resolved imaging. And then the most advanced case, you can do angle resolved imaging also with the most sensitive detection, the most sensitive detectors. And so that's the most high-end system that you can have.
Okay, thank you very much. So I think there is 1 or 2 more questions that you could answer, perhaps.
Okay, yeah. So what parameters involve plotting the intensity mapping for the PMT imaging? And so, let's see. Yeah, so I don't know exactly what you mean with parameters, but the and so the PMT image after acquisition is mapped or shown automatically, and so I think I mean what is important for intensity mapping in the end are the dwell time and the current and the voltage that you are using, because that determines the say the noise level in the image. And so, but the visualization of that is rather trivial. I think so. There's another question. What is the CL intensity difference in page 23? Oh, whoops. Yes, and so in this antenna, you see this intensity difference if you map if you map it with the electron beam, and this in fact represents the standing wave that you have in this structure. And so this structure is it acts like an organ pipe. It acts as a resonator where the waves rattle around, and this modulates the electric field inside of the structure, and also it modulates the local density of optical states. And so if you are in a maximum in the standing wave pattern, the probability that the electron transfers energy is increased, and that's why you see a maximum there. And so you're actually imaging sort of the standing wave pattern, because that is the local density of optical states is proportional to that. And so the fact that you can see that is why the cathodoluminescence is so interesting for nanophotonics and plasmonics.
And I guess there is a question, Tone, in the chat box, if you can see it. Can you see that?
Let's see. Oh, yeah. So how much, there's a question on how much we can rely on the absolute intensity, and can we interpret the intensity as we do in a UV vis spectroscopy? Yes, and so this is a very good question. It's quite a long answer, but I'll try to compress it. And so in UV vis spectroscopy, you have a very well calibrated source, and so this can be used to quantify things in a very quantifiable way. If you do cathodoluminescence, you can quantify the electron beam current that you have with a Faraday cup, and if you do that, you can know the number of photons that you detect per electron, and so that can be quantified. And this is something that we can do very well in our system, also because we have a very good way of reliably aligning it. Because if you have measurement A and B and the alignment was different, you maybe in measurement B you lose intensity, and so then you cannot compare measurement A and B. But in our case, because we do the alignment always in the same way, then if you know the current that you are using, you can compare measurements in terms of intensity, and say, for example, that sample A is more efficient in terms of light emission than B. But to quantify things in absolute sense, so relative sense is easy. To quantify things in absolute sense is more difficult. And so in the end, you will get a number that specifies number of photons emitted per electron. But this is, you have to somehow convert that into something that is meaningful. And in most cases, this is not in the end not the number you're interested in. But in relative terms, it's very useful. And so you can, in that sense, you can easily compare it.
Okay, great.
I guess there's also a question on pricing, and I think for that I will refer you to talk further with the sales people from AXT and Delmic.
Yeah, thank you so much, Tone, for all the answers. I guess in next couple of days, we will get in touch with you guys to first thank you for attending and also to ask you for your feedback. So any feedback would be very, very valuable for us, because this, as I mentioned earlier, was the first of its series. So we're going to do this more regularly, and we would like to bring topics that are really interesting to you guys. So if you have any feedback, please send that to us. We will definitely use it to make this more useful for you. Another thing is that I think for the first webinar, this was very, very successful. So again, I should thank you all for attending. Hopefully we will do this in a very regular manner, and we will let you know about the rest of the topics we can go for. So to continue this discussion, we have actually the topics that that Tom showed on his last slide. So if you are interested in any of those topics, please let us know. We can kind of tailor the next webinar around that topic. And also, if you want this presentation be done for your group or friends who couldn't attend, again, let us know. We can easily arrange that. And that's something that we would love to do, and we will do. So if there is no other question, I think we can maybe end this session. So I'll wait maybe for just 10-20 seconds. If there is any question popping, we will attend. Otherwise, okay. Thank you all again for attending, and I hope that you all enjoyed it. Thanks, and bye.